Recording is rolling. Today is Tuesday, August 30th. So I'm not going to be here tomorrow. You guys are going to have to substitute. I'll get you guys set up with something that'll be worth the time. I have written your guys' quiz. I will get that to you guys on Thursday. So this will be a take-home quiz. You guys have a few days to do it, but it should be plenty good. And then you guys remember I'm picking up you guys' homework on Friday, and for you guys, conceptual, that's just going to be, you guys remember this page? It has these questions on one side. We answered a few of these yesterday, and it just said whichever ones we do in class, just follow along with me, and then get credit with those. But really, your main focus is this side with these 20 conceptual questions. We're about to do all these today. We're going to do these Kahoot style. So as we're going on Kahoot, just follow along with the questions. You get all these answers. Okay? And then that's what I'm picking up on Friday. Okay. But let's look at the starter question right here. Suppose you're down near ground level and you throw a ball straight upwards at 30 meters per second. Okay. So throw a ball straight upwards at 30 meters per second. Now, maybe you know you're on Earth and you guys know gravity is pulling downwards at 10 meters per second squared, right? That's free fall gravity, free fall acceleration. So I've got three questions. One is, what is the hang time of the ball? What's the total time of the balls in the air? Next question is, what is the maximum height of the ball? And finally, what is the speed that the ball is crash landing when it reaches back to ground level? I'll give you guys a minute to think about those. You guys see that green poster up there? So the three kinematic equations can answer any of these questions. Yesterday in class, we did simplified versions of those. So if you were, if you missed class yesterday, you guys were out, look for that rocket launch. Got delayed. You guys know I record all these class videos and put them on Google Classroom. So you guys can get yesterday's notes on Google Classroom. All right. Did anybody figure out the answers to any of these questions? Answers to any of these? Okay. I'm going to walk you guys through the answers a couple different ways. And I should tell you guys too, this question, exactly the way I phrased it, is going to help you out on some of these Kahoot questions coming up too. Okay. So one way I'll walk you guys through is just step by step. I'm just going to take this picture, copy paste it right here. Got a ball going up at say velocity equals 30 meters per second. Okay. Then 1 second later, maybe it's about here. Then 1 second later, here. Then here. 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 All right. And I know if I take a picture every single second, it's going to look almost exactly like that. Here, how did I know that? Because walk you guys through step by step. I think you guys can get this. 1 second later, how fast is it going? It was going 30 meters per second. Guys, when a ball here, guys, look up here. Give you guys all the answers that's gonna be on your quiz. Yeah. As the ball is headed upwards, is it speeding up or slowing down? Slowing down. Slowing down. At what rate? Gravitational pull, 10 meters per second squared. Right? Which means after 1 second, it's moving how fast? 20 meters per second. And then 1 second later, how fast? 10. Yeah, then 0 meters per second. Right? And then falling down. Negative 10 meters per second. And then 20 meters per second. And finally, 30 meters per second. And you know what? Actually, right there, that is the answer to one of the questions. Take a look at this last question. What is the crash speed? Oh, that's it. That's it right there. Right? It's going 30 meters per second down. So that's the answer to the last one, right? How about these other questions? Right. Ooh, hang time of the ball. Now, if you guys followed the story I just told you, then how many seconds was the ball in the air for? 4. 6. 6. You guys see it takes 3 seconds up and 3 seconds down, right? 1, 2, 3 seconds to reach the peak. 1, 2, 3 seconds back down. So that's 6 total seconds, isn't it? You see that? Okay. And finally, maximum height. Okay. Here's one way you can get maximum height. Could you split this problem in half and say whether the ball was on the subvert path or if you look at the second half of the story, when it's coming back down, right? Either way you do it, what's the speed at the very top? 0 meters per second. And I care about that because maximum height, I care something about that point, and I know something very special about that point, and that's that there's zero velocity, right? So you can solve this one of two ways. You can say you throw the ball upwards so that it has zero final velocity, or what I think is maybe a little easier conceptually is if you just look at the second half of the problem, you say, hey, what if this was a situation like you drop a ball off a cliff, and you say, how far has it fallen in how many seconds? 3 seconds. You see that? Because it takes 3 seconds to get back to the ground. Right? Like splitting this whole problem in half. Right. So do you guys remember yesterday we used a simplified version of that first equation, kinematic equation? We said something like this. The height something falls, if it's released from rest, is just 1/2 gt squared. You guys remember that? It comes from here. You need a review from yesterday. Right? The first equation is the only one that tells you something about the relationship between how far and how much time, right? Displacement time. The other two don't have both x and t in them, but the first one does. Okay. And then v naught is initial velocity. If that's 0, which maximum height situation is going to be 0 velocity at that point, it's that x equals 1/2 at squared, right? And then instead of x for general displacement, I'll use h for height, and then for acceleration, I'm going to use free fall gravity. So that's why it looks like this. Okay. Then let's plug in some numbers. We got 10 meters per second squared and 3 seconds of fall time. If you go from the maximum height back to the ground, see, we find that changes the displacement. Right? That's a 3-second fall. Guys, what's 3 squared?
9.
9. What's half of 10?
5.
5. What's 5 times 9?
40.
45 meters. Okay. So this ball fell 45 meters during these 3 seconds. Therefore, didn't have to go up 45 meters, like thrown from the ground. Right? Okay. So there you go. There's all 3 of these questions answered. Now, let me go back and answer these a different way. And that's to stick to those formulas and make equations. But we sort of did that with this maximum height question already. Okay. But hang time of the ball. So here's there are lots of ways to solve these, but we'll just do one way. Hang time. Aren't you going from the ground back to the ground?
Mm-hmm.
Okay. So, guys, what is the displacement from the ground to the ground?
0.
0, because you're back where you started. Right? Remember, displacement, you don't care about. Displacement is path independent. All you care about is starting point, ending point. If you're at the ground, Okay. So, and if the question is hang time, well, we're back to displacement and time. I care about something to do with this equation. It would say gt squared, something like that. Okay. Where this would be 0 from the ground back to the ground, to be meters, right? 0 meters. Okay. I know I threw this thing up at 30 meters per second. I'm trying to figure out what is hang time. You guys know the answer to this already is 6 seconds, right? 1, 2, 3, 4, 5, 6. I'm just showing you guys different path through the woods to get to the answer. This is ultimately going to be 6. Okay. But how can you show that? Okay. Plus 1/2. Right. Now here's where there's this little technical detail. Guys, if you throw the ball upwards at 30 meters per second and gravity's pulling downwards, then I actually have to plug in what number for this G? Not positive 10, but negative 10 meters per second squared, so that all my signs are consistent. I throw it one way, but gravity's pulling the other way. T squared. Okay. Is that okay? All right. Again, you already know what the answer to this is. It's going to come out to be 6 seconds. I'm just showing you a different way to get there. Okay. Hey, do you see 3 terms? Boink, boink, boink. Can I divide everything by t? T. Guess what's 0 divided by t? 0. What is what is this expression? Just 30? Be like well,
It'd still be over most seconds, right?
Yeah, meters per second, and then divide by seconds. I guess that'd be like meters per second squared. Okay, and then this meters. Hold on a minute. Something's weird. Oh, no, sorry. Just plain meters per second. Made silly. Okay, because t's cancel. Okay. And then over here, half of -10 is -5. So it'd be -5. And then one of these t's cancels. I still get a t. This would be meters per second squared here. There we go. Solve for that t. Okay. So I'm tagging on the units because it's pretty good practice to do that. If that totally confuses you, just focus on the numbers. You'll still get it right though. Okay. 2 algebra steps away. Guys, should I add the 5t over? Get 5t equals 30. This be meters per second squared. This guy's meters per second. Is that okay? And then finally, do what to both sides to solve for t? Divide by 5 meters per second squared. So divide both sides by 5. 30 divided by 5 is 6. And then meters per second divided by meters per second squared. The meters cancel. One of the seconds cancels. The other one flips back up on top. Becomes seconds. 6 seconds. Which again, you guys knew was the answer to this question from the outset. But there's one way to get it for equations. Okay. And what about what is v crash? V crash. Okay. Well, since we know the time now, could you use maybe the second equation? Maybe this is not even the only way to do it, but this is one way. I want the crash speed. I know the throw speed is 30 meters per second. I know acceleration's down 10 meters per second squared, and I know the whole thing was 6 seconds, right? Let's try that. So let's go. Crash speed or crash velocity is throwing velocity plus at. And I'm going to modify this a little bit. I've got v naught, say minus gt. I consider you throw upward, but it's pulling downward. Okay. So crash velocity is equal to 30 meters per second minus 10 meters per second squared times 6 seconds. Okay. Guys, what's 10 times 6? 60. And that'd be meters per second. Okay. What is 30 minus 60?
-3.
Negative 30. Aha. Okay. So the crash speed is 30 meters per second, and the negative for the velocity part tells you the direction, says it's in the same direction as gravity, which is down. Okay. And you guys knew that already, because you guys remember we just solved that a few minutes back by like stepping through it step by step. You guys said, oh, it's got to be going down 30 meters per second. Okay, because it went 30, 20, 10, 0, 10, 20, 30. Just remember that? So different ways to get there. Okay. And well, okay. I think that's all right, right? Okay, you guys get it? So lots of what we just killed these questions, lots of different approaches, and they all kind of converge on the same answers, regardless of how we approach them. All right, you guys ready for Kahoot? Kahoot. Yeah. All right, and you guys got those conceptual questions out, so you can follow along. Make sure you're getting these. At classic. All right, there's your pen. All right, so I think we got about everybody here. All right, if you're still a little bit late, then see that 6-digit pin that should show up at the bottom of the screen once I hit start. All right, you guys got those conceptual questions out? Gonna follow along? All right, which is the homework then we gotta pick up this Friday, right? So you guys know we're knocking out the homework right now, the main part of it. Right. You might see some quiz questions that look like these. All right, here we go. One possible unit of speed. Yeah, all those will work. So miles per hour, that's what we use in the States. Right? Hey, kilometers per hour. If you cross over the border to Canada, you probably use kilometers per hour. Light years per century. And if you think about it, isn't that some kind of distance per time? Just like all these are formatted distance per time. That technically works, doesn't it? Right? You know what else you could use is meters per second. right? Which you guys used in your lab recently, meters per second. That's the one we usually use, right? All right, but all those check out. They're all some kind of distance per time. All right, Leia leading the pack. Object moves 5 meters in the first second, 5 meters in the next second, 5 meters in the third second. What is acceleration? Ah, 0 meters per second squared. Right. Well, sort of a trick question, kind of, right? Because the more obvious question would have been, what's the velocity? And what would the answer to that question have been? What's the velocity? 5 meters per second, right? So it's always accumulating 5 meters every passing second, right? Velocity is 5 meters per second. But you guys see that that velocity is not changing? It's 5 meters per second, then it's 5 meters per second, right? So it's always accumulating 5 meters every second. The fact that it's not changing means 0 acceleration, right? 0 change in velocity. Okay. Is there a question about that? Why the answer is 0? Okay, because constant velocity. Okay. All right. Next one. Oh, Luca, take top spot. As an object falls freely in the vacuum, what is increasing? Oh, one winner. Yeah, velocity. Velocity is increasing. All right, so let me definitely switch my screen back over. Remind you guys of something here. So do you guys remember? I know this goes back to last week. Dropping a ball off a cliff. Right? But this is a pretty fundamental graph in this class that ties all these equations together. Dropping a ball off a cliff. We did a table of values. We did some graphs. Right? Let's look at this table of values. So here's the time taken, time in seconds. 1, 2, 3, 4, 5 seconds. Okay. What are these other columns? What's the acceleration? What's the velocity? And what's the displacement of the ball from the top edge of the cliff? Okay. So acceleration. Hey, doesn't gravity always pull it 10 meters per second squared? Regardless of how fast it's moving, regardless of how far it's fallen, regardless of how much time it's spending, right? It's always 10 meters per second squared. I should tell you guys that's strictly true in a vacuum. So, right, but what about velocity? Isn't velocity picking up 10 meters per second every passing second? Velocity is changing at a constant rate, right? But that one's picking up, right? And then displacement is the 1/2 at squared one, right? Where it goes further. Okay. All right. So acceleration is constant. Velocity is increasing at a constant rate. Okay. You guys get it? Is there any question why the answer is velocity is increasing? But
I thought when it said like a vacuum space, like if it falls, if nothing can fall. In space.
Oh, okay. Yeah. I get what you're saying. So in this context, vacuum just means there's no air drag. Yeah, but you can have a gravity pull. All right. Luca, Darcy, Carson, Elon, and Leah. Top 5. Ball's thrown straight upward, and it's caught when it comes back down. In the absence of air resistance, its speed when caught is what? Its speed. Yeah, the same. The same as when it was thrown upwards. Okay. Now the opposite direction, right? But it's the same speed. Okay. You know what? Didn't we just do that a few minutes ago? If you throw it up at 30 meters per second, slower, faster. Remember, these two speeds are going to be the same, right? For the same elevation, right? If you throw it at ground level and you catch it at ground level, right? Wouldn't that be true? Okay. In fact, right? Is that okay? So switch over. If you guys have any questions about these, let me know too. Luca, still in the top spot. A ball thrown upwards rises and falls back to the floor. During this time, acceleration is always directed downward. Guys, which way does gravity pull all the time? Downward. When the ball is moving up, is gravity pulling down? Yeah. When the ball is moving down, is gravity pulling down? Yeah. So acceleration is always downward, right? Suppose you go 300 kilometers, takes you 5 hours. What's your average speed?
How many people are playing?
I think most of the class, right? Yeah. So guys, if you go 300 kilometers in 5 hours, if you divide those numbers, does that divide out to 60 kilometers per hour average? 60 kilometers per hour. Ball is thrown straight upward. At the top of its path, its instantaneous speed is what? Yeah, 0 meters per second, right? The problem we solved earlier today, right? That helped us out because if you ask the question, what's the maximum height? You know that the velocity at that point is 0, so you can actually use that to plug numbers into equations. Right? 0 meters per second at the very top. A ball is thrown straight upward at the top of its path. Its acceleration is what? Ah, 10 meters per second squared. Because the entire time it's in free fall, gravity is always pulling down at 10 meters per second squared. It doesn't matter if the ball is moving up, moving down, moving fast, moving slow, even moving to the side, which we're about to do like next week, projectiles. Gravity, when it's in free fall, which means that it's only the only force acting on it is its own weight. Right, gravity's always pulling down at 10 meters per second squared. Right, even at the very top of its path, when it has 0 speed. Still accelerating down, 10 meters per second squared. A car accelerates 3 meters per second squared. How long to reach 15 meters per second? Yeah, 5 seconds. There you go. Right. So you guys are probably looking at that second kinematic equation saying, well, 3 times 5 is 15, right? So 3 meters per second per passing second multiplied by 5 seconds brings you up to 15 meters per second. Okay. That's it. A little division to get the answer, but that is it. You guys got it. Luca, top spot. Aaron on fire. Darcy, Jackson, and Ian rounding out top 5. Freely falling object starts from rest. After falling for 5 seconds, its speed will be about yeah, 50 meters per second. The answer is actually on one of these posters. Got on my there you go. You guys see this big old poster right here? Right. Hey, look at this table. It sure does look a lot like that table you guys have in your notes from last week. So falling for 5 seconds, 10, 20, 30, 40, 50 meters per second it picks up to. Yeah, so that's you guys hear that? So 10 times 5 is 50. Look at the speedometer of a moving car. You see that car's what? Instantaneous speed. You see the speed at that very moment. Right? The speedometer tells you how fast you're going at that very moment. Okay. So if you think at average speed is more like I went several hundred kilometers and it took me some number of hours, and sometimes it was going fast, sometimes I was filling up the gas tank and I was stopped, right? Average is like total value. Right? But instantaneous is like at that moment, which is what speedometer tells you. Right? If you pick the yellow one, that's the odometer, not the speedometer. And if you pick the green one, a couple of you guys did, then, well, you could calculate acceleration using the speedometer. You'd have to pick 2 different speeds, 2 different times, divide it out. Right? But yeah, it directly reads you, the direct reading you get is the speed at that instant. Instantaneous speed. Car starts from rest. After 5 seconds, picks up to 30 meters per second. what was the car's acceleration to get there? Yeah, 6 meters per second squared. Isn't that the second equation? You just say 6 times 5 is 30, right? If you pick up 6 meters per second every passing second, that's how fast the speedometer needle is moving, right? And you do that for 5 seconds, right? 6 times 5 brings you up to 30, and then the units are meters per second. Is that okay? It's the second kinematic equation, right? Yeah.
Are you gonna put this on Google Classroom?
Yeah. So I'm recording this right now. This will be on Google Classroom. Right, here. Let me do this too. Just switch over real fast, just to put this on paper. So there's three kinematic equations. The second one answered the question we just did. Right? If the car starts from rest, what is the initial velocity? 0. So this boils down to the simplified version. This is kind of some stuff we did yesterday. It picks up just AT, okay, if you start from rest. Okay? We're going 6 meters per second per passing second. That's called 6 meters per second squared. And if you do that for 5 seconds, that brings you up to 30. And the unit is meters per second. 6 times 5 is 30. Okay. All right, back over. In a vacuum, objects fall at constant. Acceleration. And on Earth, that acceleration is about 10 meters per second squared, right? But it's not constant velocity, because it doesn't velocity pick up like 10 meters per second, 20 meters per second, 30 meters per second, right? Faster, faster, faster. Right? Now you could say the rate change of velocity is constant, but that's what acceleration is, right? Acceleration is constant. Velocity will change. Drops of water fall from a leaky faucet. What's it look like? Ooh, all right. Get further apart. Let me flip my screen over and show you guys why that's the case. Sure. Oh, ooh, actually, the answer is already kind of embedded in the work we did earlier. Okay. Guys, see this ball falling? What if you just replace the ball with like water droplets? You guys see how like spreads out, right? So, or if you want an equation, it's displacement is related to time squared, so that as it's falls further every successive second. Okay. But let's look at like an animation version of this. Suppose you guys are like animating something. Right, you want to animate a leaky faucet. I'm going to draw 3 faucets side by side. You guys tell me which one looks the most realistic. Right. So the one on the left, maybe I'll do something like this. One in the middle, go something like this. One on the right, maybe something like this. Okay. Which one of those looks most realistic? Left, center, or right? I think the one on the right. Yeah, so it's like drip, 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 drip. Yeah, the one on the right. This is it. There's your leaking faucet right there. Bing. That's the one that makes sense. Okay. Because if it's equal intervals of time that's the water droplets are falling, then it will spread out just like in the notes last few days. So 1/2 AT squared is displacement. So twice the time is 4 times the distance. Bob can jump off the ground with twice the jumping speed of Alan, just after his feet have left the floor. Yeah, Bob's downward acceleration will be equal to Alan's. Right? See, once they're both in the air, then they have the exact same acceleration, which is just down at about 10 meters per second squared. Right? It doesn't matter how fast they're going. It doesn't matter what direction they jump. It doesn't matter how massive they are. Right? once you're in free fall, you're accelerating down 10 meters per second squared. Right. Oh, Aaron, taking the top spot. What is the value of G at Earth's surface? Yeah, about 10 meters per second squared. If you want more precisely, it's about 9.8 meters per second squared, but more often than not, use that right there. 10 meters per second squared toward the Earth. Is there any question why it's not one of the other ones? I think everybody should have gotten that one right, right? Right. Got 3 winners in here. And Luca has the top spot. Ball is dropped from the top edge of a cliff. Each second, its speed increases by how much? Ten meters per second, right? Isn't speed increasing 10 meters per second per passing second? There.
I did click that one. Oh, I didn't.
The screen over where? Here it is. Here it is. Okay. Here. So the last 2 questions, the question before this one was, what is acceleration? It's always 10 meters per second squared, regardless of anything else. Right? That's a free fall. And then do you guys see the speed is picking up by 10 meters per second per passing second? Right? Goes hand in hand with that, right? All right, back over to Kahoot. Drop a feather and a coin in a vacuum chamber. Which will reach the ground first?
Oh my God.
Okay, so the key here is a vacuum chamber. Guys, vacuum chamber. You know what? I think I can dig up a video for this one. Find these lessons, motion. Aha, I got it right here. Got it right here. You guys see the feather and the hammer? Okay. Now, since he's on the moon, there is gravity. It's really weak, but there's no atmosphere, right? There's no atmosphere, so that means there's going to be no air drag. Let's see, feather and hammer. Here we go. How about that? They did hit the ground at the same time. Oh yeah. Up here. So there you go. Everything accelerates down 10 meters per second squared on Earth. Luca, top spot on fire.
Actually, my name's Luca. I put my name too.
A projectile fired straight upward, 30 meters per second. The total time to return to the ground. Uh, 6 seconds. Hey, isn't that what we just spent like the first 5-10 minutes of class doing? There. I see a couple of guys remember. Let me flip over and remind you guys. Okay. So this. Okay, so here's your guys' starter question. If you throw up at 30 meters per second, is there? And then where's my other notes on this? I did some work here. Oh, where'd it go? It's just disappeared. Well, I guess so. Crazy. All right, so you guys remember it slows down to 20 meters per second, then 10, then 0, then 10, 20, 30 meters per second. How much time does it take? 1, 2, 3, 4, 5, 6. It takes 6 seconds, right? Okay. Yeah, so if you look at your notes from this morning, I think the leprechaun just stolen from me. Yeah, you will see that it takes 6-second hang time if you throw upwards at 30 meters per second. Right. We solved that with equations earlier today. All that. There you go. Right. Computer's super laggy. All right, yeah, we're still good. Last question. Suppose a jumper claims a hang time of 6 seconds. Oh, that's like we've been solving this. If that were true, that's kind of ridiculous, but suppose it was true. How high could that jumper jump? Oh, 45 meters. Oh, here's my notes. Found my notes. Okay. Please switch back over and show you guys why 45 meters. Because we also solved this one earlier today too. Right? Guys, remember throw a ball upward to 30 meters per second. Here's the full scenario. Okay. And one of the questions was, well, what's this height? What's this height? Okay. And one way of solving it, here's like a simplified version, is if you cut this problem in half, say, well, how far did it fall during those last 3 seconds, right? 3 seconds up, 3 seconds down. 1/2 AT squared. Here's your acceleration, here's your time. Boink, boink, get 45 meters. You guys remember that? Okay. You know what? Let's solve this in a different way. Could you take advantage of, say, this one right here? You guys see this third kinematic equation? Just get past the time value. Let's try it that way. Let's do VF squared, because I want you guys to see that you can solve these problems lots of different ways. So VF squared equals V naught squared plus 2AN. Okay. And then, guys, if you throw a ball upwards and you're looking for maximum height, what is the speed at that moment? 0 meters per second, right? So you can take advantage of that and plug in 0 meters per second for that. Squared equals, threw upwards at 30 meters per second, squared plus 2. I'm going to call this negative 10 meters per second squared. I'll call this H max for the x. That's what that would correspond with. Right? Okay. 30 squared, that's like 900. Subtract that over. Negative 900 equals 2 times 10 is 20, net off the negative, times H max. Guys, what is 90 divided by 2? 45. The negatives cancel. Most of the units cancel except for one of the meters. That's meters. Equals H max. Ah, there you go. So there's a different way to solve the problem, right? You guys have seen multiple ways to solve this now, right? So if you guys get a quiz question like this, well, you guys have multiple approaches.
Oh, when's the quiz?
Oh yeah, the quiz. I'm gonna get you guys the quiz on Thursday, and that'll be a take-home quiz. So you guys have some time to do that. All right, let's see who won. Who won the Kahoot? With the bronze, Darcy. With the silver, Luca. And the gold, Aaron. Or Arian. Runners up.
Hey, runner up.
Jackson and Ian. All right. Okay.
Griffin.
Yeah.
Over time, like speed run it, like go as quickly as you can.
That'd be pretty fun, but we gotta solve some more problems with you guys. And so switch the screen over. Down away. All that stuff. All right, so last few minutes of class here. Let's do some problems on this page. We did a couple scenarios yesterday, so let's do some more. How about number? Let's straight down and let's do 7 and 8. Number 7 and 8. So this is one scenario. A ball is dropped off a cliff of some given height. Okay, so we know the height. On an alien planet. So we're leaving Earth. We're going to an alien planet, which means we don't know what the gravity field is. And somebody times us that it takes 8 seconds to reach the ground. The fact that you drop the ball means you know initial velocity is 0, right? Okay, so you have 3 values. You know the height of the cliff, you know how much time it took to reach the ground, and the fact that you dropped it, right? And you're trying to figure out what is the gravity field of that planet, so it falls off that cliff in that time, right? And also, what's the crash speed? Yeah, so everybody has different numbers, but we all have the same scenarios. So if you look at your number 7, number 8, you also have an alien planet, okay, but you might have a different cliff height, the whole deal, right? So, I'm gonna, well, okay. We got 4 minutes. Oh yeah, go ahead. That paper.
We can give.
Okay. Alright, anybody needs the paper? Here you go, right here. Okay, you need the paper. Okay. So the fact that you have the height of the cliff and also the time, you guys see only the first kinematic equation has both the displacement and the time in it, but the bottom two don't. Right? They have one or the other. So the fact that that's true, I'm going to use the top one. In fact, you know what else? The fact that you release the ball from rest, what happens to this term? Goes to 0, doesn't it? Right? So couldn't I just boil this down to, instead of x, I'll say h like a height change equals 1/2 a t squared. Is that true? Okay. So you drop a ball, it falls this height, and some amount of time. We'll see out here. Okay. And we're trying to solve for this acceleration. Now you know the height change. On my paper it says 24 meters. And we're trying to solve for this acceleration. This all reaches, the ball falls down to the ground, and according to my paper, well, my paper says 8 seconds. Okay. Now let's think about this for a moment. Guys, if you drop this ball on Earth, 24 meters, wouldn't it definitely reach the ground faster than 8 seconds? Yeah. So for it to take 8 seconds to reach the ground, I'm thinking gravity on this alien planet is what really large or really weak. I'm thinking there's going to be a really weak gravity field. We say less than 10 meters per second squared. Let's find out. Multiply both sides by 2. 48 meters equals a times 8 squared is 64 per second. Okay. Divide both sides by 64. Acceleration is, over 48 over 64 is, meters per second squared. Good number for that. I'm looking at 0.75 meters per second squared. Yeah, so this gravity field is extremely weak. That's a tiny, tiny planet. Maybe it's like some little moon or a big old asteroid or something. Okay. And the follow-up question says, what's the crash speed? Okay. So we need the acceleration to answer that. Let's go forward with that. I can tell you a couple ways to solve this and just do some time. You go, the velocity it picks up to is just acceleration times time. It starts from rest. So 0.75 meters per second squared for 8 seconds. Just using my numbers from before. Okay. I'll see what that would be times 8. That's 6 meters per second. Okay. Or I could have solved this a different way. I could have used this third kinematic equation. Let me try that and see what would happen. Now, V0 is still 0, so that piece goes away. So I could have said final velocity squared equals 2ax instead. Now, I know what the answer is. I'm just showing you guys that there's a different way you can solve this. So 0.75 meters per second squared. This time, the height of the cliff was 24 meters. That's from before. Just use the same number before, right? Do you guys see the one algebra step is you need to square root both sides? Square root both sides? Is that okay? Df equals the square root of all this fun stuff. 2.75, 24. That'd be some number of meters per second. I hope the answer is 6. Let's see if it is. 2 by 0.75 by 24. It is. It is 6 meters per second. Exactly the same number we got using the other method. There we go. 2 different ways to get there. All right. Any questions about today? All right. So I will not see you guys tomorrow, but I will see you guys on Thursday. Yeah, you guys have a great